So in order to talk about the electric field, very important concept, let's talk about what we already know. If I have a sphere and it has some charge associated with it, and I bring another sphere nearby it with a test charge, positive test charge, then there's going to be a force pushing away from the large sphere. Suppose for a second now that I take away that little test charge Q0, and I just mark that point, and I say this is point P. Now I know that if I put in a test charge there, that there's going to be a force on it. I have some knowledge of what's going to happen at that point right there. So what's really going on is this body A is setting up what we call an electric field in the space that's around it. And we can kind of probe this electric field by putting in point charges. If I put in a point charge right there, I know that there's going to be a force in that direction. Kind of the same over here. I can kind of map out where the forces will be given where I put my test charge. We're going to define this electric field. It's going to be a vector. It's going to be the force that is felt by the test charge divided by the test charge, or essentially K multiplied by Q. It's going to be the charge of the sphere divided by the distance of separation squared. What we can then do is we can say this electric field is going to exist whether I have this point charge or not. If I know what this electric field is at that given point there, and I say, you know what, I'm going to not put Q0 here, but I'm going to put, say, Q2 in right there, then I can figure out how much force Q2 is going to have. Force on Q2 is going to be the electric field that exists whether there's a charge there or not, multiplied by the charge that I've inserted there, Q2. The direction of the force is going to be in the same direction as the electric field. Suppose I now put in a negative charge. As you can see right there, the electric field is still going to point away from this object. The force, however, is going to be the electric field multiplied by negative Q0 is what they're calling it now. So the force, as you can see, is going to be in the opposite direction. It's going to point towards the sphere, kind of like you'd expect. So how do I go about setting up the definition of an electric field? Well, first I'm going to have my charge, and I'm going to put that kind of right there, and then I'm going to set up a distance vector, call that r, and it's going to point in a straight line from the charge that I'm interested in into that point P. Now what I'm going to do is I'm going to say, well, I know that if this is a positive charge, I'm always going to use a positive Q0 for my test charge. I put that guy in there. What is the direction of the force? I know that the force is going to be related to the electric field multiplied by the test charge that I'm kind of sticking in there. So if I put in a charge of Q0, it's going to be the force that I feel is going to be the electric field multiplied by Q0, and I can figure out that the electric field is going to be equal to K multiplied by the source charge right there divided by the distance of separation squared, and this is a positive charge, so the electric field is going to point away from the positive charge. Now if I say, well, what does the electric field look like if this is negative? Well, I do the same thing. I set up a unit vector and I put in my positive test charge. The positive test charge is going to feel a force towards the negative charge. What that tells us is that the electric field is going to point towards the negative charge. So in general, if we draw a positive charge, we're always going to draw the electric field as pointing away from it. So these lines right there represent my electric field. If we put in a negative charge, we say which direction is the electric field going to be in. The electric field is always going to point towards negative charges, as I've kind of shown here. So let's take a quick look at calculating an electric field. Here I'm going to have a negative charge. It has a charge of negative 8 nanocoulombs, and I'm asked to find what the electric field is 2 meters away from it. I know that the electric field is going to be equal to K multiplied by Q divided by the distance of separation squared, where K is going to be 9 times 10 to the 9th. The charge is going to be 8 times 10 to the negative 9th, and that's going to be divided by 2, quantity squared. So it's going to be 72 on the top and 4 down on the bottom. The electric field is therefore going to be, forgot my negative sign on my charge, negative 18 newtons per coulomb. The units of electric field, if you think about the electric field being equal to the force divided by the charge, unit of force is going to be newtons, unit of charge is going to be coulomb. Other thing to kind of think about here is I've calculated just the magnitude of the electric field. The direction is going to be, in the negative direction. If I define my vector r hat to be the unit vector, kind of in the line between the two, I can kind of put my r hat on here. So here I've calculated my electric field in terms of the r hat vector. We know everything we need to know if we want to break that up into the x and y components. We can use this concept of electric field and its relationship to force when we start talking about distribution of charges. For example, suppose we have a battery and we hook it up to 2 parallel plates. What's going to happen is this parallel plate is going to have a bunch of negative charges on it. This one's connected to the positive terminal, so there's going to be a bunch of positive charges on it. And we know that the electric field is going to go from the positive towards the negative. It turns out that it's going to be uniform. We'll see why in a couple of slides here. Now suppose I take a negatively charged electron and I put it between these 2 plates. Well, what's going to happen is it's going to feel a force. And rather than saying I'm going to calculate the force from that negative charge and that negative charge and that negative charge and that negative charge, I can say I know that there is an electric field. I'll show you why it's going to be uniform in a little bit. And if I know how much that electric field is, turns out that it's related to the voltage and distance of separation. We'll talk about that in a couple of chapters here. It's going to be 1 times 10 to the 4th newtons per coulomb. I can say how much force is that charge going to feel. Well, it's going to feel a force of its own charge multiplied by the electric field. Since the charge itself is negative, it's going to be in the opposite direction, so the electric field is going to point upwards, and the force felt by the negative charge is going to be downwards, essentially being forced away from all these negative charges over here. Now, I've already talked about what happens if I have say a charge right here. I know that I'm going to feel a force due to Q1 and a force due to Q2, so it makes sense that if I take away my charge and I just look at point P, I'm going to have an electric field right here from E1, which is going to be equal to K Q1 divided by R squared, and there's going to be an electric field due to charge 2. Rather than being away from it, it's towards it because it's a negative charge, and that's going to be K Q2 divided by R squared, and I'm getting my direction more or less from the charge itself. We can add those together, using vectors, much like we do with forces, and we get the net electric field right there. If you want a little bit of practice doing this yourself, example 21.8 has an electric dipole, just breaking things up into components. So we can use this superposition of electric fields to look at the electric fields caused by real large physical objects. For example, a ring down here. We're going to say that this ring has a charge Q associated with it, and we're going to start to look at the electric fields from each and every single tiny little chunks of this ring. So we'll be looking at the electric field caused by this little tiny amount of charge dq. How much charge? Well, if we say I'm going to take the total amount of charge in this ring and divide it equally over the circumference, so 2 pi a, where a is the radius, 2 pi r, I'm going to call that my linear charge density lambda. So really this dq is going to be equal to the linear charge density multiplied by ds, which is the size of this segment that I chose. How much electric field am I going to feel at some point P? Well, you can kind of see we've drawn this little tiny electric field. We're calling that dE, and that's going to have two components, dEx and dEy. We can kind of conceptually say we know that dEy is going to cancel out, because if I choose another section of the ring down here and say how much electric field am I going to feel, you can see it's going to be pointing right along there, and that's going to have a component in that direction and a component in this direction. The x components will add together, the y components will cancel out. So really all we're left with is dEx, and if we know what that angle is, we can say that's going to be dE multiplied by cosine of the angle. We can now write the magnitude. dE is going to be essentially be k dq divided by r squared, where we can write r as the distance from the ring to the point P, as well as the radius using trigonometry. And since that's an r squared, we're left with k dq divided by x squared plus a squared. And I'll tack on my cosine of the angle because it's just in the x component right here. Now we can do two things. We can say that the cosine of the angle is going to be x divided by the radius, or x divided by x squared plus a squared to the 1/2 square root. And we can also say that dq is going to be equal to lambda ds, and we can rewrite the electric field now as k lambda ds multiplied by x divided by x squared plus a squared, now to the 3/2, where I'm essentially combining this 1/2 and that component down right there. Keep in mind this is actually dE. To get the value for E, I need to integrate this guy, so my electric field is going to be the integral of all those dE's. And what I'm integrating is I'm integrating over ds, so right here, and I want to integrate around the ring. So I need to go from 0 all the way to 2 pi a. So those are my limits of integration, 2 pi a and 0. And fortunately, all of these parameters can be pulled out, and we're just left with ds on the inside. Other problems, you won't be so fortunate, and you'll actually have to go ahead and do an integral. So this is going to be k lambda x, and then I have my x squared plus a squared to the 3/2. The integral of lambda ds from 0 to 2 pi a is just going to be 2 pi a, and we can combine lambda and 2 pi a to get our q. So k q x divided by x squared plus a squared, now to the 3/2. That's going to be the electric field at point P. The interesting thing is, suppose x is really large, then a is going to essentially be small. As x gets large and large and large, we can even say a would be, nearly 0. And what this is going to boil down to is at large distances, large radiuses, we're left with kq over x squared. Here's another problem, example 21.10, where you actually have to use calculus, and you have to say, you actually have to do an integral. Essentially you set it up the same way, where you look at some tiny little piece of this uniform plate and say that it's going to cause an electric field dE, going to have the same type of symmetry where you can kind of see that the y components are going to cancel out. And we set it up the same way. We say dE is going to be equal to k dq divided by the radius squared. figure out what we're integrating over. It would be negative a to a in this case. And really, I'll let you take a look at this. Highly recommend you take a look at this problem as well as the next one. I'll save my lecture time for working some problems in the back of the book. Another very important example, uniformly charged disk. Another important example that uses the superposition of electric fields, and it's going to be super important to what we're going to be talking about in the next couple of chapters, which is capacitance, the electric field between two infinitely large charged sheets. This is only valid if this distance of separation is fairly small, which, for everything we look at in this class it will be. We know from example 21.10, 2 examples ago, that we could write that the electric field from an infinitely charged sheet is going to be equal to its charge density divided by twice the permeability of free space. What we can now do is say, let me take a look at this sheet right here. This sheet has some negative charge density associated with it, so I know that the electric field is always going to point towards it. So I can write the electric field 2 is always pointing towards it right there. Sheet 1 has a positive charge density, so the electric field is always going to point away from sheet 1. And we can convince ourselves that these two are going to add together. They're going to have equal magnitude, simply opposite directions, and the electric field will be 0 outside of this configuration. Same down here at the bottom, they'll add together and we'll get 0 net charge, or 0 electric field. In the middle, we're going to add these two vectors together, and we're going to simply say that that's going to be 2 sigma divided by 2 epsilon naught, and we can get the electric field inside the capacitor here to be simply the charge density divided by the permeability of free space. We can visualize the electric field by using electric field lines, more or less imaginary lines that follow or let us map out the electric field. So for example, if here I am at point P and I say I'm measuring my electric field and it's in that direction, or at point O, my electric field will be in that direction. At some later point, point P, my electric field will be pointing in this direction, and at some later point, point R, my electric field is in that direction. Then I can say I'm going to create this imaginary line that's going to connect all these 3 points and say that my electric field is more or less flowing in the direction of the line that I just illustrated in blue. We can use this concept of electric field lines to start to look at the interaction between charges. If we consider just what the electric field lines should be for a positive single charge, we know that it's going to point radially away from it, kind of as such. And electric field lines are not going to convey necessarily so much the magnitude of the electric field, just the direction. So if we picked this point right here, the electric field is going to be rather large. Pick this point out here, it's going to be rather small and pointing away from it. However, the closeness of the electric field lines is going to give you an indication somewhat of the force. The more densely packed in they are together, the larger the electric field is going to be. Similarly, if I drew a negative charge, the electric field lines are going to all point radially towards it, just for an isolated point charge. Now, if we consider a system that has a positive charge here and a negative charge here, we know that the electric field lines are always going to point away from the positive and towards the negative as such. However, they're going to add together in regions in between them. The electric field right here is going to be the sum of that of the negative charge and the positive charge. As we start to look at various other points here, the electric field is actually going to bend around and have lines that are flowing more or less from the positive to the negative. As you can see right here, that's more or less due to the sum of those two electric fields, and we get electric field lines are kind of a map of the electric field as such. One important thing to keep in mind is electric field lines can never intersect. You're never going to see them cross over. If we look at the interaction between two positive charges here, we know the electric field is always going to point away from these two positive charges, so kind of like that. These electric field lines are never going to intersect, and so we're going to essentially reach a tangent line right here and leave kind of a dead space in the middle where the electric field is going to add up to be 0. Another interesting concept is that of an electric dipole. Essentially, electric dipoles are going to be two charges. They have to be opposite signs. They are separated by some distance. I'll call that distance d right here. And here I'm going to have my positive charge, and here I'm going to have my negative charge. I'm going to define an interesting quantity which is called the dipole moment, which is going to be the charge multiplied by the distance of separation, and it's always going to, much like the electric field, point from the negative to the positive. So there's my dipole moment, P. One interesting thing that is a dipole but is also electrically neutral is water. Water is going to be two hydrogens and one oxygen, hydrogen having a net positive charge, oxygen having a net negative charge. You stick them together and you have something that has 0 net charge. However, there's a whole bunch of chemistry that dictates that these two hydrogens are not going to be in line with the oxygen. They're actually going to bend off at some angle, meaning we're going to have more positive charge on this end of a water molecule and more negative charge at this end of a water molecule. So we have a separation of charges at some distance, and we're going to have a dipole moment. What this also means is if you try to dissolve something in water, some things are going to be attracted to the positive end of it, and some things are going to be attractive to the negative end, and it's actually going to be a great solvent. It's going to dissolve, say, salt quite well. Now if you take a dipole, a separation of charges, opposite charges, and you stick it in, say, a uniform electric field, you can see the electric field lines right here. Obviously the force is going to be in that direction for the positive charge and in this direction for the negative charge. Equal force, simply opposite directions. You know that's going to create a net torque. It's going to be a force times the distance, and we can actually cause this dipole to start to rotate. So take a quick look at this example 2131. And lastly, take a look at example 2114, which is going to talk again about the superposition of electric fields for, in this case, a dipole.